about a very different type of grassland, perhaps, the Alpine tundra that we study at the Niwot Ridge LTER. So among the LTERs, Niwot Ridge is the only high elevation mountain site. And it was in the first cohort of sites that was funded starting in 1980 by NSF. So it's 43 years old this year. And the data sets, some of the data sets that we have and monitor, especially our climate and water data sets, go back even further to the 50s, even when some scientists at CU Boulder started doing some monitoring that we have maintained since then. We currently collect and curate about 42 long-term data sets that range to be documenting everything from water quality, runoff patterns, to pika demography, snow and ice patterns, of course. And then my favorite are the alpine plant community and population abundances. We have about 20 really invested faculty at CU Boulder and elsewhere that span the gamut from microbial ecologists and evolutionary biologists to ecosystem modelers that are all working together to try to understand how these alpine ecosystems tick and how we can go about predicting and hopefully helping to conserve how they're responding to climate change. I've got this problem with, I couldn't move it. Something was blocking my ability to advance. Okay, so a little bit more about our site. We're located in the Front Range of Colorado, in the Southern Rocky Mountains, about 25 miles northwest of Boulder, Colorado. We're on the taken lands of the Arapaho, Ute, and Cheyenne peoples. And right now, the main kind of research site that we study spans about 4 square miles from the Continental Divide all the way down to the subalpine forest. And so this spans from about 10,000 feet in elevation to 12,500. The majority of our site is actually on U.S. Forest Service land. A little bit of the land is actually owned by CU Boulder, but most of it is Forest Service property. So the key resources that might be relevant to the people in this audience that are partners in conservation and management in this region are interested in are particularly water, ice and snow, alpine lakes and streams. We also have a pretty unique biodiversity in the alpine tundra plant community. The tundra is just the open grassland that is above tree line. And so that's kind of most of where our site sits. But we do have long-term data sets and projects going on in the subalpine immediately below the tundra. And we have a lot of really neat high elevation mammals and other wildlife. And again, these plant communities that I'm so fond of. So this is just a slide showing some of the large numbers of stakeholders and other partners that we have that we collaborate with from local, regional, and national agencies and organizations. And they're kind of scattered throughout all these different categories that I'm showing here, but perhaps most relevant to this audience are these ones in kind of the bottom right corner. And these are relationships that we're actually very actively trying to deepen and broaden right now, being kind of up in the mountains, away from most of the local towns and organizations. We don't have a lot of direct connection at our site with a lot of these people. So we're really actively trying to engage them and find ways to better connect the research that we're doing to the information that these partners need to know. And we're also trying to learn more from them in terms of the kinds of questions that we should be asking and addressing at our site. So it's worth noting that kind of how we, the alpine tundra grasslands are maybe a little bit different than some of the other grassland sites that exist in the LTER and that we've heard from today, and that we don't do a lot to kind of directly and actively manage them. We're not burning them, we're not grazing them, we're not doing much to try to control invasive species. We don't have a lot of invasive species. These are largely systems that we think of as kind of relatively intact. except they're being very dramatically affected by these larger scale human impacts of things like climate change and acidification. And so we're really trying to understand the impacts of those kind of global drivers on the dynamics that we see locally at Niwot Ridge. So these the ecosystem functions that alpine systems play around the world, particularly in the state of Colorado, are large and important. The most well-recognized one that most of our partners are often the most interested in seeing our records and learning about is water. Mountains are called the water towers of the world because they store water in the forms of snow and ice every winter and even across years. And then that snow and ice is what's kind of gradually released over the course of each summer to become available deeper in the watershed. And Niwot Ridge is actually part of the city of Boulder's watershed, and a great deal of the area that we study actually falls within those watershed boundaries. And so we work pretty closely with the city of Boulder in terms of sharing records and kind of information about the timing and magnitude of snowmelt and runoff every year. So it's worth, I think, mentioning that more than half of the world's rivers originate in mountains, and mountains supply clean water to half of the global human population. But these regions also provide really important habitat for biodiversity that are really broadly adapted to these extreme environments. And in Colorado, alpine and mountain regions are a really important source of recreation for the general public. I think our ski industry generated over $1 billion last year, and we had about 15 million skier visits. So people care a lot about their mountains in Colorado. So the kind of really kind of big footprint in this system is winter. The cold season, its length and its severity is really what drives so much of the ecology and ecosystem functions in this system. So we have these very long, cold, harsh winters, along with high solar radiation, super windy up there, lots of desiccation stress. So we consider this a pretty extreme environment. And given the importance of these particularly cold conditions and the roles of snow and ice in driving the ecosystem services and just overall ecology of the system, there's a lot of concern about how mountain systems in general are if they're particularly sensitive to climate change. And there's also some evidence that this phenomenon called elevation dependent warming, which is this, there's some data that suggests that with increased elevation, the rate of warming is actually increasing as well. So not only may these systems be more sensitive to rising temperatures because cold matters so much, but they also might be experiencing faster rates of change than a lot of other, than lower elevation sites. But something they have kind of to their advantage is that they're this very rugged terrain, and this topographic complexity provides a lot of kind of microhabitat heterogeneity that's potentially providing some buffering effects in the responses. So lots of refugia, for example. And so even going just from the south facing to the north facing side of the mountain can lead to a very different microclimate. So something we're really digging into right now at Niwot is trying to harness this topographic complexity and understand how it mediates the overall response that we're seeing to climate change and the ecosystem services that the mountains provide in the face of climate change. So not that this probably needs to be said, but climate change is happening at Niwot Ridge as it is everywhere else. We're seeing an increase in our maximum temperatures since about, over the past 70 years, we're seeing about 0.5 degrees Celsius per decade in both our alpine sites, which are the really high sites, and then the slightly lower subalpine sites. This is happening in mountains everywhere, but we're a little bit unique from other parts of at least the Intermountain west of North America in that we're not seeing a drastic shift in the total amount of precipitation we get every year. And so there's a bit of a step function in the late 1970s that had to do with kind of a global atmospheric shift that's not related to climate change. But other than that, we've been pretty flat. And so we're getting about the same amount of precipitation in our little pocket of the Southern Rockies. And it's not just Niwot Ridge, it's kind of our little part of the Southern Rockies. But so we're kind of haven't quite tipped over that edge that a lot of the other parts of the Rocky Mountains and also the mountain ranges along the West Coast have really starting to see where they're seeing declines in snowpack and earlier snowmelt. So I think it's just a matter of time, but so far we've not seen a major decline or change in our precipitation patterns or amounts. Important though that even if we're still getting the same amount of precipitation, and about 80% of that is snow, warmer snow is very different than cold snow. It's heavier, it's wetter, it doesn't blow around the landscape as much, so we don't get those deep snow beds that often can hold water for us late in the summer. So our runoff patterns can be more kind of homogeneous and synchronized and fast in the spring. And from kind of an ecological perspective, the kind of homogenizing of the distribution of snow across the landscape takes away a lot of the kind of heterogeneity that we think helps maintain biodiversity. And so there are some plants, for example, that only live in the very windswept parts of the landscape that never accumulate snow. And then there's other species that specialize on those deep snow beds that maybe only get, out of the snow for a month or 6 weeks out of the year. So the warm snow is different than wet snow. So even if we're still getting the same amount in total, the nature of it is likely changing. So we've used some ecosystem modelers. I really thought I would be better for time. So I'll kind of just go through this. We're doing some modeling to try to predict how snowpack is going to change. As I mentioned, it hasn't really happened yet. And we're working with some collaborators at NCAR, so the National Center for Atmospheric Research, to kind of model these physical, chemical, and biological processes operating in these terrestrial systems. And so with this graph on the left here, quickly what it is showing, we have the day of the year, and this is predicted snowpack over that year. We see that through time, so starting at the top, we decline in the total amount of snowpack, and the timing of the peak of the snowpack is also shifting a bit as well. And if we use these models to kind of run simulations through time, what we found is that in our part of Colorado, we're just now starting to get to the point in these model predictions where the signal of a longer growing season is actually going to be able to start separating from just the noise in the model predictions. So this is consistent with that prediction that we're slowly moving, or we're about to kind of emerge to where we're seeing a decline in our snowpack and longer growing seasons or more snow-free days. So we're trying to monitor this and understand the effects of shorter winters and longer summers on our systems. And one thing we're doing is we have a bunch of cameras out that monitor individual plots. You can see the little blue flags here. See some researchers coming in and out to survey those plots. We're actually kind of quantifying the green up and the green down to characterize the timing at which we are seeing this growing season play out, but then also how much total biomass is being produced and if that changes. And we know that this depends a lot, again, on where we are in the landscape. So this is some more modeling predictions by Katya J, who's a wonderful postdoc on our project. And the dashed lines here show south-facing slope model predictions, and the solid lines are north-facing slope. And these are 3 different meadow community types. And so the main difference here I want to point out is we see a huge difference in the length of the growing season, depending on if we're just on one side of the mountain or the other. And so that fine scale topographic heterogeneity has really important impacts for kind of our overall predictions for what warming is doing to the growing season length. We've also been doing a series of large-scale experiments to quantify the effects of this extended growing season We use open top chambers to increase air temperature within vegetation plots, and we can build snow fences to actually add snow to kind of simulate the other effects on plots and monitor its effect on vegetation. And most recently, we have just been wrapping up a giant experiment where every year we'd go out to 5 different locations across the mountain and spread black sand over the snow a little after peak snowpack, and then monitor these different plots in terms of the plant communities, the biogeochemistry, the insect predators, the phenology of the plants, keeping track of all of these things and how that change in snowmelt timing plays out. And this is a slide, if I can get it to go. We're actually not trying, yes, I'm not going to be able to get it to go. It's hiding from me behind. Hold on. We weren't trying to monitor this through this video, but we ended up doing it. Over on the top right here is a black sand plot where we spread out that sand, and you can see that early melting out. And then the control plot is off here to the left. We've added some open top chambers. But again, you can see that heterogeneity that plays out that really shapes a lot of the overall patterns. So I think I should wrap up quickly because I've gone over already, I think, but I'm hoping that I was able to tell you a little bit about what we're learning of some of these grasslands that don't experience direct management, but that are still really mirrors of the effects of climate change on these systems. So I want to thank you for listening and leave you with this photo of a sunset on Niwot Ridge in the winter from our Tundra Cam. The website's down here at the bottom, and when it hasn't been damaged by the wind, which happens every few days, but we get it back up and running, you can log in there and control the camera and look around the ridge if you want. You might even see a few researchers up there. Thank you. Sorry for going a little long.
Thank you, Dr. Emery. That was great. You're actually spot on time, but I'm glad you wrapped it up spot on time. So I appreciate that. We do have a minute for a question to follow up specifically on Dr. Emery's. If anyone has one, maybe jump off mute or on camera real quick. If not, actually, I was going to ask one. I was really, so you mentioned that Niwot Ridge is part of a U.S. Forest Service property, I believe, a National Forest Service. So I was curious about your working relationship with the Forest Service and kind of what their, I guess, potentially management concerns or just how they're perceiving needing to steward that land into the future.
Yeah, that's a really great question. So the Forest Service is very interested in the work on the subalpine forest, and our lead researchers on the forest, they do study things across Colorado, like responses to fire and things that are directly relevant to Forest Service management. So they have a pretty direct collaboration. In terms of the tundra part, I would say our closest management partners are really the national parks. So the Rocky Mountain National Park I can see it from the top of Niwot Ridge. It's right there. And so they really care about biodiversity. Gosh, just like Jesse was saying, we are having shrubs expand across the tundra, which is a major problem. And so they even have like some of the small mammals that we monitor, they're trying very hard to protect and conserve. So there's a little bit more of them directly asking us for information that might inform things they do in terms of managing how tourists are getting through the park and anything else they can do in terms of some kind of management practices in those systems.
Wonderful. Thank you so much for that. And a big thank you to all of our speakers.